Hey, I'm in it. My bright orange shirt.
Did you?
I love that. Is this the particle?
Yeah, right. When you even explain what it is.
There's one light ball floating around in it.
Where did you get this? I want one.
Oh, yeah.
The dollar store?
I should bring like 6 of this.
Yeah,
We would never be able to get back to the subject.
no, not
It
even.
is our subject,
This is our subject?
yes.
Like the
That's what I'm
camels and the scarecrows?
So
Okay, so we're gonna start talking about more particles in the box today. Is that what I read in the email?
No.
I saw the email that we sent to delete it. And then the other one.
Wait, what did the?
I don't know how to mute. Oh, I will mute my for a second.
A box.
That's okay. So what do you see? How do you interpret?
It is a container holding a small particle in it.
Oh,
Particle in a sphere.
And when you shake it, it gets excited and lights up.
Melody, that was so good.
so it's main principle of quantum dots. One of I had a colleague who was preparing like far in the far past, preparing the thesis, and colleague same as myself is not native speaker, and the colleague hired a professional editor to just catch typos. And the professional editor was not was native speaker, but not natural scientist at all. So how was the thesis? Well, almost nothing to fix, really well written. But I found one error. You put particle in a spherical box. I think it is an error. Box cannot be spherical. I went through the thesis and corrected particle in a spherical container. So particle in the box is a concept, is a terminology, and it should be used this way. So how many dimensions? I hope you don't associate this nice toy with a coronavirus, right?
No, it's
Good.
just fun.
Not at all. I love it.
So how many dimensions does it have?
Infinite.
It's a whole bunch.
No, but if we are just blindly thinking of not blindly, like our regular Cartesian, like
Yeah,
three.
three.
So it's 3-dimensional.
You're counting time as a.
And why does it have these hairy things? What does it correspond to in chemical? From the chemical point of view, like boxes, particle in the boxes, often done was with solid semiconductors. But
Magnetic field? Magnetic field?
I think much out of the box. Yes, there is a area of science where people bring as a demonstration hedgehogs and tell us it is a magnet. And then we are not so far
This is the
yet.
hedgehog.
And then call it as magnetic skyrmions with magnetic field coming out. But this is it's more chemical. So these little hairy things symbolize a word that you guys know. Why soap is soapy?
Surfactant?
Yes. So
Oh,
Surfactant.
I've never heard that one.
Melody, please teach us.
surfactant is a molecule that is hydrophilic on one end and hydrophobic on the other end.
Oh.
That's why surfactants are typically soaps, because they can hold on to the oils in your hand and be washed away with water.
Oh. When did we talk about
Got the class.
in this class?
Yeah.
Yeah, I remember, I said
Maybe
it.
just work.
So
I don't think so. I was gone.
Maybe, I don't remember what that was.
the confined small size particles of solid semiconductors are very fun science and technological components. Like you can go into Best Buy and buy QLED TV,
Yeah.
which is quantum dot light emitting diodes. So this little pieces of semiconductor, but to process them chemically, to grow them and then analyze, one needs to make them. What does chemists say about milk?
Emotion.
Oh my God.
Colloid.
Colloid, thank
So-
you.
So it's not a solution because particles are big, they are just suspended. So in order to make semiconductor, which is like heavy, solid, with fluid in the liquid, to make a colloid, you need to put surfactants, right? So this is a model of a quantum dot. Well, so to say. Mm. So what are we going to do, and what is the goal of this meeting and the lab tonight and your homework, which is due on what?
Right.
Friday, yes.
Heard that it was due today. I told him it was.
No, nothing is due today.
Yeah.
Only fun is due today.
I am going to, I have
We're
exam on
certainly having
Friday.
fun. Only fun. Well, conflict.
Fun times, guys. So is this like a micelle?
No. Micelle is, the word micelle is used when one is speaking about like big particles of like 100 nanometers. And on 100 nanometers, you don't have much of quantum properties.
What is Sam doing? He's breaking it.
Tearing surfactants of making it insoluble.
Tearing it off, what?
Yeah.
But he just did.
Content.
Yeah.
Okay, guys, come on.
So
Quantum dots time.
Okay, kids. Okay, children.
what we were talking about, can
Yes.
Oh, thank you.
Quantum dots for children. David's first quantum mechanics, quantum dots. Yeah.
The boxes that we considered last time were one dimensional, right?
Yeah.
And if you want to apply them to real world, one needs to add like, not only X, but Y and Z. And then if we are speaking about conjugated oligomers,
Is the box technically two-dimensional because it has an X and an X and though?
well,
Or is it just a particle moving like along a
But
one dimension?
particle movement along.
It's, yeah, it's evolution over.
So and selected dimension. But if you really want to describe our real world objects, we need to bring in not only X, but Y and Z.
Okay.
Our favorite conjugated oligomers,
Yep.
they have like certain lengths along X, and then along Y and Z, the electron is confined. It is not allowed, or it's energetically unfavorable to go away, right? So it is like the box, three-dimensional box is like box for ski, right? So something really elongated or poster tube. So it's like analog of conjugated oligomer. But one can do the not cubic but square boxes, like pizza boxes, right? So pizza box would be two-dimensional.
Yeah.
Because electron goes in X and Y and confined in Z. And what are the analogs for pizza boxes are coming in science? Not like when students have a snack, but what does it correspond? Are there any analogies? Can you give an examples of scientific pizza boxes?
I have no idea, I kind of was something.
What did meant that about?
What like if we wouldn't have tablets and write on a paper, what what do we write with?
Stone.
Pencil.
Graphite.
Graphite, and if it is a single layer,
Hard.
Carbon sheet.
there is a word.
It's not graphite.
Graphite is like many layers.
Graphene.
Yes,
There we go.
so graphene is a good pizza box.
Oh,
pizza box. Graphene equals chemical pizza box.
Yes, someone please write that down.
Okay.
And
Hold on.
there are more, there's like the whole science of two-dimensional materials. When they see consequences of this, when something electron is not allowed to go somewhere, people tell confinement, quantum confinement, because electron is quantum and it is confined. So poster tube, pizza box, and the next one is a regular U-Haul box, right? If the box is very big, then it is any solid semiconductor.
That scares your gun back.
If it becomes really small, then it is three-dimensional, approximately equal in each direction, and one would call it quantum what?
Chemistry.
Mechanic.
Quantum dot.
Yes. So
Oh,
if you
yeah.
take a pencil and make a little mark of the infinitesimal size, you call it dot. They are so small, they're typically like 1, 2, 3 nanometers in size. So for bird's eye, they're just a dot.
Is this a quantum dot?
Later, second to last slide, or the very last slide will be le plus quantique.
What?
Wait,
C'est la vie.
Do you know much French? You speak some French? Not really.
I'm pretty sure.
Non, je ne parle français. Un petit peu.
That's some French to me. I don't know any French, so.
But when I try to speak in Paris to servant to the museum, asking something, she speaks to English now. We want to eat or drink. So
That's what they know. It is.
Yeah.
Yeah. So I'm just gonna
Like, this
speak
is
English.
easier for you.
French people do not care.
if our conjugated oligomers are one-dimensional, because one dimension is active. Pizza boxes are two-dimensional, right?
Whoa.
Because two dimensions are active. Big boxes are three-dimensional. But if size in each dimension is really small.
It becomes fourth dimension.
No. Oh,
I do.
there is an agreement to call them zero dimension. Because like electron goes nowhere. It is confined in a very tiny space. And yeah, to a dot. So zero dimension. Mathematically, it may be not correct, but it is already accepted
Conceptually.
terminology.
Just pretend that it is.
So we go for the Friday homework that we will do in fine details during the lab is the following. You will like it.
Okay.
Oh, well, no one likes an effort. You may not like the procedure of getting it, but the outcome
That would
will
be super exciting.
apply to your brains and hearts as young scientists. So the nature of sciences and chemistry in particular is synthesis and characterization, right?
Yeah.
Finding structure to property relations. Agree? So you modify stoichiometry, size, and then you get some signatures, which can be what? Yes, property of characterization of a molecule.
What about it? About them?
When you are in a wet lab,
Yeah.
you either purchase Sigma Aldrich or you do your personal synthesis and purification of us like monodispersed sample molecules or some materials. And then you start putting a cuvette with this material into different instruments. And you're getting characterization, you get properties.
Oh, yeah. So like what kind of property?
Exactly, yes.
like infrared spectroscopy.
Perfect. Infrared spectra, what else?
Like molecular weights, we just got a GPC.
Okay, yeah, molecular weight, infrared, and yes. So you've got the idea, right? So structure is your chemical composition and property is like infrared spectrum. Last time we were talking about cyclic voltammetry, right? So
And I was poorly trying to explain it.
perfectly, better than anyone else in this room. With guarantee.
Oh, better than we did.
Thanks.
So this is another form of characterization. So cyclic voltammetry corresponds to density of states. That is another concept that you probably remember in the middle of the night.
What?
Density of states,
What?
when you wake up, middle of the night. That's what you're gonna
I
say.
wake up in the middle of the night and I'm terrified.
Density of states.
No.
Yeah, we're thinking plane waves. when we
Yeah,
wake
I'm
up in
thinking
the middle of the
plane
night.
wave.
Yeah, we gotta switch to density of
I'm
states.
thinking about the crumbling of society. around
What
us.
about density of states? Just density of states?
Density of you're watching on one of the density of states like this.
The cells.
Quantum objects, quantum models do have multiple solutions. They have like levels, orbitals, and each orbital has energies, right? And if the amount of orbitals is too high, too much, one cannot think of them individually. One needs to compose them together into some continuous distribution. So density of states look like a spectrum, but it's more like spectrum of quantum states. Make sense?
So each like X coordinate is a different quantum state, basically.
He doesn't.
It is often hard to separate variables there, but yes, sometimes it is possible to associate several quantum states with certain dimensions, but it is too much to declare it as a general rule. So any quantum system has one set of levels, and by looking on this values of energies, their offsets and general trends of how energies are aligned, it is like a spectrum. By looking on a spectrum, you can identify which molecule it belongs to. By looking on cyclic voltammetry, you can tell whether it is ferrocene or just pure water or whatever.
Yeah.
Hexane, right?
Yeah.
To some level. Yes?
Mhm.
So Fred is also doing voltammetry.
No.
Not yet.
Fred's not. No, Fred has a different project.
Okay.
I'm the only one, me and Wyatt are the only ones that do cyclic
Voltammetry.
voltammetry.
Okay, so but structure is number of active dimensions. Property is density of states. So we need to establish structure to property relation. We will look through. We do not specify stoichiometry because shape and size sometimes is more important than stoichiometry. So we'll assume some material, maybe semiconductor, maybe polymeric, enclosed in a box of certain shape, and then the goal is to establish correlation between density of states and the shape. To be able, like, from density of states to recover shape, or from shape to recover density of states. Okay? We are done. You're ready to do the homework.
We're experts.
Yeah.
The meeting is done. This way.
Let me try. I do not know how to bring it.
It's really upsetting. Imagine basketball, but with that.
You had your chance. Let Elsa have her chance.
Yeah.
Chill out.
Put your hood on.
So
Oosh.
I will try to bring a second camera each other meeting. But now I need to humbly refocus on the board.
Oh, boy.
And-
Inception. Whoa. Gotta go down.
It doesn't want to go down.
Uh-huh.
It loses control.
Does it not like the control? It really, no, it really does. Or it just really wants it.
Give yourself a high five.
But it really doesn't want to go down. It does, much better.
Yay.
Now
That's
we
pretty.
can focus into.
Oh,
Okay,
nice.
yes.
There we go.
We should do a
Infinite high five.
video clip. It will be like a logo of the physical chemistry class. Okay.
I love it.
Share screen.
I love the lag in the reflections.
Yeah.
So, we spent time on informal chatting and got general idea. I'm not sure if I will have time to write on the blackboard, but hope that you have enough energy and enthusiasm not to fall asleep in the remaining half an
I
hour.
think we'll be fine.
Okay, this is a image. This is a like snapshot from the defense of the last student from my group who defended, and you see that particle in the box is something.
Aaron Ford.
Okay.
No, I just read the name.
That can be not only like
Are those lima beans?
Hmm?
Are those lima beans?
almost
These are so good.
Different orientation.
yes. So it will be not only studying in the class, but also you can get through profession. Yes. So here is the three-dimensional box, and it has orbitals. And remember when we had one-dimensional particle in the box, it did have single humps and two humps, and you did superposition. When you study atomic orbitals, and I see Sam has a periodic table, which is really great.
Yeah, it's kind of where.
So, tell me, please, what is Aufbau principle?
The Aufbau principle is
Take it away.
that's Hund's rule.
You can just start giving,
The Aufbau principle is not that
The lower states, the energy level, the lower states are few first. Orbitals, electrons are fused.
lowest orbital first.
Yes, lowest orbital first, energy level, lowest orbital first.
Thank you. So one is two is two,
Yes, one is two.
two P6. Okay. So S orbitals are like spheres, P orbitals like dumbbells, right?
Yeah.
Even if you do not have atoms, if you have only a particle in a cubic box, here are S orbitals and here are three degenerate P orbitals and N orbitals. So if we clearly do three-dimensional boxes, we will have an analog of atomic orbitals, right? Because the nature is the same. Okay, and here is the density of states. Like as we go to higher energy, there is a more and more states. And one can get a doctoral thesis out there. Yes.
I've always thought particle in the box is within 0 and 1.
Huh?
Particle in the box is within 0 and 1. I thought you were illustrating particle in the box.
Uh-huh.
I thought it was within 0 and 1.
What do you mean 0 and 1?
That's energy.
Energy.
Sorry, that's it.
So here is the code that you will be running during the lab and for your homework. Here is your maybe least pleasant, most challenging homework due next Wednesday. So please try to assign a couple of hours during the weekends.
This is the hardest one
Yes.
ever.
It's not the hardest, but it.
This is scaring us so that we don't take a test. This is
You
the
want
one.
a test?
No.
No,
But we'll do like self-grading, do not fear much of the grade, but try your best to do.
Okay.
My parents are coming over this weekend, so
Yeah.
I would like to ask for an extension on that.
Sunday.
It's on Wednesday, it's
My
on
parents will not
Wednesday,
leave
Sam,
until
not
Sunday.
Monday.
But you can plan on
Then do-
like half an hour each morning, waking up at 6 to
Yeah.
investing
Yeah.
30
You wake
minutes.
up at 10 o'clock.
Oh, yeah,
You
it's
got
on
time.
And I hate, but
But
who will,
respectfully, no.
we need this collective activity of grading each other. If I would be grading in person, I wouldn't care, but we need.
I'll be getting it done anyway. I just wanted to see if you'd say yes or not.
Yeah, I gotta.
Oh, so it was a little provocation and challenge, like to see how I'm saying no.
Yes.
Okay.
What?
Thank you.
Yeah.
I'm excited to be voting on our final after this program.
I think we've already done it.
The official vote.
We can.
How about right now? Who wants to do it not a test?
Oh, okay, I like it very much. So,
Melody, did you vote?
She does, she
democracy for science.
Yeah.
Maybe if you pay
So,
attention, you would know that.
Here,
Pay attention to you.
here is what we are expected to do, right? In series,
Problem.
and density of states is the latest concept that we got, right?
Yes.
So we did, last time we did density of states for one-dimensional box. It looks like, sail.
Yes.
For yeah.
Come sail
Oh, yeah.
away.
Yeah.
Sail away.
Yeah.
Sail away.
Here is,
That should be.
just tell me what you see.
Are we making that?
I see a.
It's a sail that's like blowing in the wind.
It's
Yeah, just sail
density
floating
of
and now
states.
it's making a pizza box. A chemical pizza
Wow.
box. Yeah. A
It's
graphene-
like, it's doing the wave.
Oh, now
Wow.
it's different. Now it's,
Oh.
now it's making like a quarter circle. Oh. That was funky.
Whoa,
Yeah, sail.
that's so cool. I like this a lot.
Then it calms down,
It is.
then it gets crazier. Oh, now it's like a stair step.
Yes, yes, perfect.
So then you see, and then it just
What's on me?
curves out like the exponential, the one over. The square root. Square root, yeah.
Plus one friend.
And if you stop it at the very beginning, you see those look like
Oh,
individual
Dunes.
levels. And then these individual levels consolidate,
Yeah,
they start going together and creating the sail, right?
yeah.
And then several sails combine together and form stair steps. And then the stairs combine together and form a square root. Okay, so in principle, your Friday homework is done. We just need to add meat to these balls, right? Yes,
so
and you need to do it yourself.
what does the pink box symbolize?
Good question.
You guys try it.
We can figure it out.
Is that the box that is that the box that the particle is in?
Yes,
Is it continuously expanding? Or is that supposed to be a representation of it
so
changing over?
this movie is not a dynamics. It is just a continuous snapshots of different models and their density of states. So it is independent calculation. One takes certain box, finds density of states and plots it. Then one just makes slightly, they continuously changing to see the trend. Okay,
Why is
Yeah.
the box expanding, but the axes are not? Like, what do the axes represent then? The box? Now they
the,
stay at 2, but like the box is growing larger.
so those are two independent images. Just
Okay.
for better visualization, they're consolidated together, like inset in one figure. So you can put cuvettes with different samples in your instrument, but the screen of the computer attached to the instrument will be the same.
Okay,
Okay,
all right.
you don't expect like, okay, I put different molecule and my screen blows up or shrinks, right? So it's the area where density of state is shown is just a screen of your instrument, and the pink box is your sample.
Okay, so it's like more of a, like, relative to the box itself.
Yes,
And-
structure to
okay.
property,
All right,
shape
yeah.
of the box determines shape of the density of state.
Okay.
And this is how the submitted homework on in 2 days from now should look like, with some comments and explanations, but basically it is what I expect you to reproduce and submit. So the individual levels for 0-dimensional, right? Then seals for poster tube, X for 2-dimensional, and square root for big 3D box. I don't know how I will feel time. All these shapes can and must be derived analytically. There are equations for this.
There's a hole in my shoe.
Oh, I feel like it should be derived. You set us up. Yeah, we were not expected to derive anything analytic. So, how do we derive things analytically? It is impossible to do in 15 minutes, but I will try my best, at least to like skim through it. There are several concepts that we combine together. One is that we do have two axes. One axis corresponds to quantum numbers, another is energy. And then we flip it over. So number of states as function of energy. So it's concept one. Second concept, when we were in one dimension, then like, remember this crazy strawman walking in over the direction? So the distance from origin, the path that this strawman walked through is unambiguous. But how do you set it up if it is 2 or 3 dimensional? So we need to do something with dimensions. And we need to count number of quantum states that this character left behind. So how many quantum states did it, he, she, this creature left behind if it is a 3-dimensional box? So we need to deal with a little bit of geometry. And for this geometry, we need your memories about middle and high school in the following aspects. What is the area inside a circle? And what is the volume inside of a sphere? You have time to record.
Area is pi r squared.
And volume.
4/3 pi r cubed.
How?
Wow.
You should teach this for at least we all know how to read it. Okay. And so the strategy is that we will develop this NOS as number of states behind the strawman, and then we will take derivative. Derivative of number of states will be density of states. And we already did it for 1-dimensional, now we need to do it for 2 and 3. Okay? I never was trying to do it in 15 minutes. When I was starting, no one cares about it. First, I started to teach a graduate course with a similar content, and this material took me like 2 hours to deliver. And then from year to year, I'm trying to squeeze it, but I'm not sure that I will succeed this time. So, okay, so if we look into 2 dimensions, there is an important thing. I still need to do one little thing before we go to this derivation. Otherwise, so 5 minutes for the board, 2 minutes for 2 dimensions, and no, 5 minutes for 2 dimensions, 5 minutes for 3 dimensions. So
Yeah.
can you dictate me your quiz mass in
So M.
2M?
There's a L on the bottom.
Yes, pi.
L squared, yes.
Enough?
No, pi.
Okay, if this is 1 dimension of size L, if it is Lx, we can add index Mx, Lx, right? Now, if it is a pizza box with Lx, Ly, suppose our particle in the electron in the box is memoryless. It doesn't, it independently moves along X and Y direction, which is okay. It's like Euler balls. One can do X, same as for projectile, X and Y components are independent, right? Then exactly what Melody was trying to say. There are quantum states associated with X dimension. There are quantum states associated with Y direction. So energy will be energy associated with X plus energy associated with Y. And for X, we will do the same. H bar squared and X squared by squared to X squared. And for Y, we will do the same, but we will do NY squared by squared LY squared. So there could be different lengths. It doesn't need to be, they do not need to be the same. And there will be independent quantum numbers. So index of quantum state is a quantum number. And to specify the energy, it will be E and X and Y. So, and there will be many states. Okay. If you have third dimension, it will be the same way. But we need to rush, and one can put H bar squared by squared to method outside of the box, and X squared LX squared plus and Y squared LY squared. Right? So how do we map this quantum state? Before we were like, here is a number of states, here is the energy. Now it is different. We need to design a space with quantum numbers and X and Y, and each state of two-dimensional box is a point on this plane. So for example, it could be no excitations, ground state in respect to Y, but first, second, third excitations along the NX. Or it can be opposite. It can be no excitations along X, but second, third, fourth along Y direction. So to specify any quantum states of this two-dimensional box, we need two quantum numbers. Right? So now, how do we teach our strong men to help us? What will be the path for strong men to walk? So Sam is showing like up, and then horizontal, then vertical.
I mean, there's on a 2D plane, it's probably like infinite amount of paths.
Right, but and it becomes unsolvable. But we do not need to compare these paths. We need to correlate number of states that have energy smaller than a given threshold.
So would it be kind of like
I don't know what you mean, but the answer can be this. Yes,
I'm just,
yes.
I'm trying
It's
to-
very, I would answer it the same way.
I was gonna say, it probably, it doesn't match up to a function, like, can it be described as like, the square root function or like, a linear function, like basically like everything under your like line is where it, like all possible like states?
I like very much what Sam is telling. It's not a complete answer, but right now we are experiencing a brainstorming effort. And if we would solve some new problem, because this problem was solved by scientists before, it is exactly the way how we would try it, but very, very right direction. So how do we find energy of a quantum state? Geometrically. Geometrically. Energy geometric. Suppose just for a minute that Lx and Ly are the same, and we leave them outside of the bracket.
You have hx squared and hy squared.
Yes.
No, that's
And just LL
that's
squared to M, and here we have an x squared plus ny squared.
So it cannot be like x squared plus y squared equals r squared.
So what is, if you have some strange space with two dimensions, what is summation of squares of two x's?
R, right?
Yeah,
It's a circle.
yes, it's radius. It's radius squared, right? So energy is a square radius in this strange space.
So we switched to, could we like
Okay.
use polar coordinates?
We can, but we can survive even without it. But yeah, I appreciate brainstorming. So
Would be-
any, if you fix the radius r, so any state with the same distance from the origin will have the same energy, right? So all dots on this line or quantum states will have the same energy. Or if they are not dense enough, we need to do a little stripe. So between r and delta r. R and r plus delta r. Okay, and if I am a straw man walking forward, I need to count number of quantum states behind this radius, independent of a path, it's just departing from the center, and I need to find the area of the space if I know the radius. So if I know the radius, the area will be equal
Pi r squared over 4.
pi r squared, and please teach us y over 4.
Because it's only a quarter of a circle.
Quadrant. What quadrant? Like quadrant.
Yeah,
Okay, right? Quantum numbers, we're not considering negative quantum numbers, they are only increase. Okay. So the area in this power corresponds to number of states. Right? And at the same time, it is the energy. Right?
so do you take the derivative of it with respect to r?
No, with respect to E, let's do very little manipulation. So if I want to just convert it back into energy, let's do manipulations. So from here, r squared corresponds to energy multiplied by 2ml squared divided by h bar squared pi squared, right? And then we need to multiply it by pi divided by 4. So pi 4 e 2 s l squared h bar squared. What is this?
Pi.
Pi. Thank you. I can read that. But
Pi squared.
thank you. So melody. So this is a constant, C. So the number of states equals constants times energy. Right? And density of states, DOS, equals DDE of number of states. So it will be
C.
constant, right? So now you remember it is a staircase steps, right? So one flat area is when the quantum numbers corresponding to out of box movement for z direction are the same. Next step is when quantum number corresponding to z increases by 1. Okay, so we did prove shape of the density of states for two-dimensional case. Right? Now, okay, everything goes on plan. Now, 5 minutes for the three-dimensional case. Four minutes, 30 seconds. So, yeah, here is our favorite character walking in this creative space, right? Here is the shape that we did. And we are looking for the area, doing this derivation, finding number of states proportional to radius squared, doing this energy radius, and then finding that the density of states is a constant. Done. Now, for the three-dimensional case, it is examples of pizza boxes. Graphene, molybdenum disulfide, bismuth telluride. I cannot pronounce it, but there are two-dimensional perovskites named after their designers. Even David Grobner is his subject for thesis, but I'm not sure if we both can pronounce. Rudolf den Popper.
Oh.
Base of a perovskite. So here is a lead core, and those are two-dimensional fields, and electrons behave there as pizza in the box. So we derive it. So if our straw man works in the three-dimensional space, we can use the same concept, moving from center outside, and x squared and y squared and z squared added together will be radius in three-dimensional space, right? So we need to look for the volume behind. So if one does the same tricks, finding radius as
The R square.
function of energy, huh?
The R square. The 3-dimensional.
So here is n and x and y and z. Right? So and x squared and y squared and z squared. It will be r squared.
Yeah. and
What's wrong?
In the 3-dimension, when you have X, Y, and Z, it's still equals R
The R
squared.
square.
Just be like on an angle.
And
Kinda, I
Because
guess,
when you switch it to polar, it still ends, it becomes R cosine, R squared cosine plus R squared sine.
and you can do the same thing of expressing radius of energy or energy of radius, right? Just square roots whenever it moves. So number of states behind the back of the straw man is the volume of a sphere of a certain radius, but we need to divide it by
Oh, well.
Eight.
Eight.
because instead of quadrant, it is octant.
Yeah.
So 4/3
In a 3-dimensional state, it's not a quadrant, it's octant.
Yes.
Cause it's like,
Is it-
if it's like a sphere. You're like.
Oh, it's
cutting
because
it
you're
into
adding
one
2 more
and taking
dimensions, so you times it by 2. Something like that.
2 to the power 3 equals 8. Well, plus and minus 2.
So you have a circle. The top half of the circle has 4 quadrants. Bottom half has 4 quadrants.
Back to the subject. We're basically out of time, but we'll squeeze it in no time. So number of states behind, we can express this time, so there is a third power, but the energy is a square. If you plug in energy, then number of states will be 3 from this cubic, 2 because of conversion between energy. So energy to the power 3/2. If we need to find density of states, out of the number of states, we need to take derivative of the independent argument to the power 3/2. By taking derivative, power of polynomial decreases by 1. So 3/2 minus 1, 1/2. So square root of energy. So the density of state for 3-dimensional box is energy to the power 1/2 square root, right? And this is how it should look at the end. Examples, moving again, moving again, moving again. End of the lecture 22. Yeah, thank you for your support, passions, enthusiasm, and dedication to the course. Looking forward to seeing you at 5 in the web.
I can't wait.
Wow, Fred just counted down the minutes.
Ready for this digging quiz?
I forgot there was a quiz. I don't know what the quizzes are, but.
I think it's just gonna be the C1 e to the lambda t plus C2 e to the lambda t.
No, I mean, yeah, I know, but I don't
with
feel
that.
good and I need to go eat something and I was gonna skip the class.
Don't
Can I
forget
get
the
Yeah.
dot.
Oh,
Elsa, we can take the quiz together and then leave.